Wireless digital communication system has become an essential part of our life, and all wireless communication requires access to parts of the radio frequency spectrum. The wireless signals from the transmitter in the form of electromagnetic wave need to transmit at a certain frequency to reach the receiver. The frequency spectrum is a finite resource, and only part of it is suitable for wireless communication. Each wireless connection will take up parts of the frequency spectrum, and as the number of devices increase, the issue of spectrum scarcity arises, which motivates the idea of dynamic spectrum access. To understand the idea of dynamic spectrum access, let's see the following example. Suppose Jonathan has bought a frequency band for receiving phone messages. We call him the primary user of the band. Jonathan enjoys unlimited access to the band and can receive messages whenever he wants. However, he does not receive messages very often, and most of the time, the frequency band is idle with no transmission occurring. So to utilize the frequency band to the full extent, he comes up with the following idea. He finds Noah, who would also like to receive messages, but Noah could not buy his own frequency band. Jonathan offers Noah access to the frequency band to also receive messages, provided that Noah does not affect Jonathan's message transmission. Noah always has messages available to be received, therefore he decided to receive them whenever Jonathan is not transmitting. With Noah's messages, the spectrum utilization is much higher. We call Noah the secondary user of the spectrum, as he has less priority compared to Jonathan in terms of accessing the band. This example forms a basic dynamic spectrum access model.
Our design is based on the following scenario. We define occupancy pattern as the time-varying bandwidth usage mode of the primary user. Here we can see the occupancy pattern has only two modes: transmission mode, utilizing the entire 1 MHz bandwidth, indicated by colored rectangular blocks, and idle mode, indicated by empty rectangles. The shortest duration for a given occupancy mode is 500 milliseconds. Our client, the secondary user, knows the probability of an occupancy mode at any given time. The performance of such system is evaluated based on both primary user and secondary user throughput. The goal of our system is to maximize secondary user throughput by utilizing as many idle periods as possible, while minimizing collision by avoiding any occupancy period where primary user is transmitting. This design is based on software-defined radios, or SDRs, at the request of our client. Software-defined radios implements communication system in software and allows digital signal processing. We use BladeRF SDRs and Raspberry Pi 4 for Linux operating system and easier access to GNU radio software.
We now discuss the technical approach taken for the secondary link design. The overall structure of our design secondary link is based on the commonly used Open Systems Interconnection, or OSI, reference model. This is a reference framework for communication between systems which splits functionalities into 7 layers. This is defined such that each layer only interacts with the layers directly above or below, and each layer has a separate and well-defined function. When one host system communicates with another, the application data is passed down through the OSI stack until it reaches the physical layer. This then transmits the information over the physical communication medium, the wireless channel in this case, to the physical layer of the second host. This data then passes back up the stack to the corresponding application in the second host. Our design implements the link layer in the bottom 2 layers of the OSI model, which are the data link and physical layers. For the secondary link, the link layer's main purpose is to make decisions about when and how the secondary user should access the channel. The link layer is implemented on top of the physical layer, which has the job of facilitating communication over the wireless channel on command from the link layer. That is, to take the binary data in the form of packets passed down from the link layer at the transmitting side and deliver them to the corresponding link layer at the receiving side. The link layer consists of the Media Access Control, or MAC protocol, and the Spectrum Sensing subsystem. The ability to monitor the primary user activity is key to enabling opportunistic spectrum access. For this purpose, we implement a spectrum sensing subsystem at the secondary user transmitter side. This listens to the channel for primary user transmissions. For our spectrum sensing subsystem design, we chose to reconstruct the primary user activity using energy detection, a technique where we monitor the average energy in a given frequency band. When the primary user is actively transmitting in the wireless channel, the secondary user transmitter will observe an increased average energy in its received signal. The subsystem then decides that the channel is available for use if and only if the average energy is sufficiently low. Both simulation and hardware testing showed that this technique was able to reconstruct the primary user occupancy pattern extremely accurately without incurring any substantial delays.
The MAC protocol of the system works closely with the spectrum sensing system. Here, we have a plot of the primary user and secondary user transmission. Whenever the spectrum sensing system decides that the primary user is not present, it will inform the MAC protocol about the availability of the spectrum, and the MAC protocol will therefore start the secondary user transmission. The transmission will now utilize the full slot, as shown by the tail gap here. This gap is controlled by a parameter called the utilization factor that is set less than 1 to reduce the likelihood of a collision with the primary user. The MAC protocol only works if the timing of the secondary user and primary user synchronizes. Therefore, we're adding a mechanism such that whenever the falling edge of the primary user occurs, we also reset the timer of the secondary user.
To transmit data through the wireless channel, it must be modulated properly in the physical layer to protect itself from possible impairments. To achieve this, the physical layer on a transmitter is arranged as follows. The raw data from the above layer will be stored in a buffer. When the transmitting command from the MAC layer is received, the buffer will send the raw data in terms of byte stream into the channel coding subsystem. Redundant bytes will be added here to help the receiver detect error or out to correct them. Next, the byte stream will be framed into packets with a header for synchronization at the receiver. Then, it is modulated before being pew-shaped to increase the bandwidth efficiency and help with the match filtering process later. Finally, the modulated signal is passed to the hardware front-end to be transmitted through the carrier frequency. On the receiver side, the received signal will first go through preamble detection and channel estimation to identify if the incoming packet is valid. Then, using this estimation, the equalization subsystem will try to undo the channel effects to an adaptive algorithm, and the signal will be match filtered to maximize the signal-to-noise ratio before going through simple synchronization to find the optimal sampling time. Next, the frequency offset between the transmitter and the receiver will be synchronized, and based on the header in the data stream, the correct frame is identified. Finally, the signal is demodulated and decoded for error, and the valid data will be fully recovered and ready to be transmitted to the next layer. Now, we will look into the simulation performance of the system that we have designed. First, the performance of different modulation schemes is observed as the signal-to-noise ratio increases. The maximum throughput is highlighted in red. It is clear that APSK has the best performance in high SNR. Next, we validate the standalone secondary user. The flow graph on the top shows our transmitter and receiver connected to the channel model. The bottom shows the domain plot with the corresponding throughput of our system. It is seen that our achieved throughput is roughly 2/3 of the theoretical due to the system bursty nature. Finally, we look at the case with the primary user activated. On the time domain plot, the burst with higher amplitude is the primary user, and the smaller one is the secondary. It is seen that they don't overlap most of the time, and both primary and secondary users have throughput.
Now we will discuss the expected performance of the secondary link. In the absence of the primary user, meaning the secondary user had access to the channel all of the time, the secondary link was able to achieve a throughput of over 650 kilobits per second. This is only 16 kilobits per second shy of the theoretical throughput of 660 kilobits per second if no errors were to occur. Now synthesizing the secondary link with the primary user system, we can evaluate both the achieved throughput of the secondary user and the level of degradation this causes to the primary user quality of service. This setup was tested for two different distances, the first being very close together, and the second being separated by just under 2 meters. For these two cases, the secondary link was able to sustain a throughput of approximately 160 kilobits per second and 70 kilobits per second respectively. At the same time, the primary link was able to achieve between 94 and 96% of its original throughput. This highlights the minimal degradation to the primary user quality of service.
The primary advantage of our proposed DSA solution is the improved spectrum efficiency and capacity. One popular area of application for DSA system is cognitive radio. Cognitive radios are software-defined radio systems that can sense its transmission environment and adapt to users' communication needs by changing its transmitter and receiver parameters to allow more concurrent transmissions. DSA solution implemented to cognitive radios can potentially improve areas such as emergency and public safety communications. In medical fields, DSA-based cognitive radios can be helpful in omnipresent patient monitoring and assist in providing time-sensitive patient information such as blood sugar level, blood pressure, and ECG to the doctors. With the explosive growth on Internet of Things applications, DSA system can help address the issue of rapidly growing demand for wireless bandwidth by the increasing number of IoT devices. Our proposed DSA solution can be expanded to address more complex industry scenarios, such as transmission in a dynamic IoT spectrum environment with multiple IoT devices. Additionally, expanding the functionalities of our MAC protocol and physical layer subsystem can allow our DSA system to be used in situations where multiple secondary users would like to share the same underutilized spectrum, also commonly found in IoT device communications. Adding collision detection on secondary user receiver and functionality to request retransmission in case of collision will further enhance our proposed solution and allow it to be used in situations involving less time-sensitive ongoing monitoring, such as smart agriculture.